That's imitating a passage that the xylophone plays in a lovely piece for strings and percussion by the Hungarian Béla Bartók, the music for strings, percussion, and celesta. It starts the sort of nocturnal, mysterious third movement of the piece. It's been known for some time that if you count the way these beats are divided up, you get a Fibonacci sequence. The way it works is simply you've got 1, 2, 3, 5, 8, 5, 3, 2, 1. It's beautifully neat, and it sounds absolutely spontaneous without being obvious what's going on. This sort of relationship in Bartók's music was pointed out quite a few decades ago by a Hungarian musician, actually, Erno Lendvai, who had slightly known Bartók, but Bartók hadn't talked about it, he just noticed it. But there are many composers who have been involved in this sort of thing, and composers, it turns out, the more you find out about them, the more mathematical their interests tend to be, even although they don't talk about it very often, because they usually think that what they do before they publish their scores is their own business, and they just want the music to sound right. And of course, there's nothing better than a golden section to make something sound right without it being obvious why, because it's that sort of natural balance that can keep reproducing itself, expanding itself, and dividing into itself, and it keeps its integrity. This is what's fascinated people, I suppose, through the centuries. Now, that example there from Bartók's music for strings, percussion, and celesta interests me in a particular way, because what it does is take equal segments, equal beats, and it divides them by differing Fibonacci numbers, so you can hear the music speeding up and slowing down again. The converse of that, of course, is that if you, instead of keeping equal segments, if you vary the segments themselves by golden section relationships, so you can have something like 5 beats against 3 beats against, or 3 against 5 against 8 against 13, or you can go into onto a much bigger scale. This is the sort of thing that Claude Debussy, the French composer, did. He's known as an impressionist, but it's rather a misleading name, and he thought himself that it was very misleading, except that he knew that the impressionist painters were very precise and methodical about what they did, and he was the same in his music. He was very interested in the visual arts. His friends were writers, painters, and a few scientists as well. He was a fascinating man, all in all. And what you find in his music is, for example, what happens in his images for piano. There are 6 of these. They're all, if you study them closely, based on very, very meticulously worked out proportions using symmetry and mostly golden section and Fibonacci numbers. 3 of them do the same thing in different ways, and it's too long to be able to show you here, but I can describe what happens. The piece starts very, very quietly. It ends again very, very quietly. It fades away almost to nothing. And in the course of the piece, it builds up to a climactic point, which is smack on the golden section of the piece, if you measure the beats and the bars that the piece is written by. This happens in 3 out of 6 of the pieces. The other pieces have slightly different shapes, but they're worked out by the same sort of mathematics. It's quite fascinating once you find what's going on. If you want to follow that up, there's a book written about it called Debussy in Proportion, fairly aptly enough. There are smaller scale ways of doing this, and this is one of the lovely things about Debussy's music. The first of these images is called Reflets dans l'eau, Reflections in the Water. And of course, that's a lovely title for what happens in the piece, because the whole piece is a sort of golden section shaped arch. But after the climax of the piece, the order of what had happened in the first part reverses itself. So the second half is mirrored, but at the same time, because of the golden section, it's compressed or refracted like reflections in the water. And typically for Debussy, he's very organic about the way he presents his material. So what you can hear immediately is, if I play you the opening bars of the piece, he gives you the shape of the whole piece in the opening phrases, like this. lovely and atmospheric. The right hand's playing sort of ripples in the water, and the left hand is sort of dropping pebbles in the water. Even Debussy said that to a pianist who was working on the piece once. He said, just imagine the pebbles dropping in and the ripples spreading outwards. Now, you can suddenly look up close at it and get out the measuring tape to the piece. And what happens in each of these phrases is that the figurations rise for 5 beats, and then they fall for 3. And then again they rise for 5, and they fall for 3. And in the meantime, the way the pebbles drop, you've got an interval of 3 semitones followed by 2 semitones. Everything is the same kind of refracted reflection as the shape of the whole piece. And you're starting with the numbers 2, 3, 5, 8, building up your Fibonacci numbers in the manner of the whole piece. And the whole piece follows that shape in all sorts of different ways. And aspects of the piece reflect themselves slightly in miniature. It's quite a study analysing how that piece is put together. There's another way in which this can be done. In one of Debussy's loveliest preludes, the famous Sunken Cathedral, La Cathédrale Engloutie, he mirrors that system there. What happens, it's the piece is based on an old legend of the drowned city whose cathedral mysteriously rises out of the waves into the mist just off the coast once a year, and you can hear the organ pealing, the bells pealing, and the monks chanting. In Reflet dans l'eau, the piece I just played a little bit of, the way it works is that the long part of the golden section comes first, you reach the peak of the piece, and then the shorter part tails off. In the Engulfed Cathedral, he reverses this because the climactic bit is a big long section where the bells peal and the organ sounds and the monks chant. And it arrives exactly at the golden section by Fibonacci numbers. It's 21 out of 55. So you've got 21 of the units, and then at the climactic point, everything opens up, and you've got 34 left to the end of the piece. I can give you the introduction, just the lead into that climactic section. And so on. It's quite magnificent. You could, of course, plant that at any point in a piece and it would sound magnificent. But it is interesting for me that he planks it exactly at the point of golden section. Somehow it just gives that the maximum impact and balance. And when you hear that whole piece played, everything just seems to have happened at the right place. You can't tell why unless you know about golden sections and measure it. Even so, he slightly hid it, because if you take the score of that piece and count the bars, it's not immediately obvious, because there's something about the speed at which that piece has to be played that only a few newer editions show, because it was known from Debussy's time. He made a recording of the piece that gives the game away, that you have to change speed at a certain place. It sounds the same speed, but it looks a different speed on the page. And once you've done that, then the piece becomes sensible to play, and all the golden section and Fibonacci number relationships fall into place, just as you heard them there. So it's at the same time simple and complex with Debussy. What you hear sounds incredibly simple and straightforward. The way it works out is extremely sophisticated. There's one other lovely example, and it's probably the most dramatic example in all of Debussy's music of how you can use a Fibonacci sequence. It's in, I would think, the most exciting of all his piano pieces, the magnificent L'Île Joyeuse. This is one that doesn't tail away at the end. It finishes in a splash of absolute glory, covering the whole keyboard, and just about the piano lid just about lifts off of its own accord because it's so magnificent. It's like the whole of his orchestral La Mer. Now, what he does in this piece is he paces everything quite steadily through the first part of it. And if you count the bars and the beats, you'll notice things are very symmetrically spaced. You don't get your golden section. And it keeps going on like this, but you can gradually sense the excitement growing until you get to a particular point where gradually things change. Now, if you look at the whole piece, you'll find at that point where everything changes is exactly the golden section of the whole piece. And then he brings in a new dynamic, literally. He gives us a series of crescendos, a short one, builds it up, then drops, and then a slightly longer one, builds it up, drops again, then a longer one again, drops it, and then the longest one of the whole lot to the climax of the piece. And you can probably guess how he measures them. You've got 8 bars, then 13 bars, then your 21 bars, and the final one is your 34 bars. A lovely Fibonacci number sequence. It doesn't draw attention to itself, it just sounds great. I'll start with the 8-bar crescendo, and you might hear me giving you a little bit of commentary about what's happening where. So it's 8, I'll be starting, the bars go 1, 2, 3, 1, 2, 3, 1, that's the speed they go at, and there's 8 of them into the first climax, and each climax gets progressively stronger as we go up. So here, starting with 8 bars. One. Bingo! Plump.
In school, in mathematics, we tend to perhaps look at certain numbers which are perhaps special. Pi is related to the area of a circle compared to its distance across, or the square root of 2 on a square. But there are other numbers that are special, and we often don't look at them at school. And one of them is the golden ratio, or the golden mean, sometimes called phi. And it's been known from ancient times, from the Greek times. It's been used in buildings, it's been used in music, it's been used even in the way that people reconstruct a face after an accident. What is it? Where does it come from? So Euclid wrote about a phi, or the golden mean, the golden section. He actually didn't use that word. Those words seem to come about a lot later. But he wrote about different ways in which you could take a line and put a point on it. Obviously there's the point we might call in the middle, the mean, but the golden mean is slightly further along. And it appears in quite a few geometrical objects, these three-dimensional objects that have the most symmetry. They have all sorts of ways in which the golden section really is in there. One of the ways to see that is actually to go back to 2 dimensions and think about an equilateral triangle where it's got 60 degrees if the sides are the same length, or a square if the sides are the same length has got right angles, and we see those around everywhere. And hexagons have got 60 degrees outside again, and we see those, we know that those tile quite nicely. But what about this gap of 5 in the middle? And if you look at a pentagon shape then and draw the diagonals in on a pentagon, where they cut is exactly at the golden ratio. And so a 5-pointed star has got golden ratios all over it, these golden means. And that was one of the ways in which Euclid was interested and came across this ratio, this mean between extremes. What happens is that if you divide the line like that, then this is the smaller one to the larger ratio, and that proportion is exactly the same as the larger one is to the whole line when you add this bit back on. And that's what defines it. It comes up in nature as well. If you're trying to think of other shapes you could use instead of a cubic dice, which has got all its sides the same length and all the shapes, all the angles are the same, all the faces are identical, so that when you roll it, each face is equally likely. The one that we usually use has got 6 faces, but there's another one with 4 faces, and they're all triangles. It's a triangular base pyramid, a tetrahedron. And the 2 largest of these, one of them has 20 sides, which are equilateral triangles, and the other has 12 sides, which are the pentagons. The icosahedron and the dodecahedron. Icosahedron 20-sided, dodecahedron 12-sided. And Euclid wrote a lot about geometry, trying to put it on a really precise basis. And some people think one of the aims of his 13 books of elements of geometry were to show that there were just 5 of these shapes called Platonic solids, after Plato, the other famous Greek philosopher. In terms of numbers, it's the square root of 5, take away 1 and divide by 2, or if you like, the square root of 5 and add 1 and divide that by 2. So the number as a decimal has no patterns in it, it doesn't repeat, it doesn't recur, it goes on forever like pi and various other numbers do. Whereas 2/3 and 5/7 actually settle down into a repeating pattern after a while. This is a number that doesn't, so we know it's not an exact fraction in that way, it's a rather special number. And the number is such that if you take 0.618 and divide it into 1, you'll get 1.618. It's the same as, so to do division, dividing it into 1, to take its reciprocal, all you do is add 1. And that's quite unusual. That's the only number where you can just add 1 onto it to get its reciprocal. The other thing is if you square it, if you take the 1.618 and you square it, you'll get 2.618. You've just added 1 to do the squaring. And from that follows a lot of properties which seem to be why nature likes the number, because it can do multiplication by just doing a simple addition. And it's the only number that has this property between arithmetic series and geometric series. The Fibonacci numbers, one of the ways in which everybody will probably meet them every day is in terms of the food we eat, or particularly the vegetables, fruit and vegetables. For instance, if you take a banana and just cut it across there, and you'll find it's in 3 little sections. Whereas if you try that with an apple, cutting across its equator, you'll find there's a nice 5-pointed star in the middle. If you look at a cauliflower and the florets on a cauliflower or a broccoli, you'll find they're in 2 sets of spirals, one in one direction, one in the other. In one of them there's about 8, and the other one there's about 13. If you look at a pine cone or a pineapple, there are spirals around those, often 8s and 13s, sometimes 13s and 21s. There are spirals on the patterns of a sunflower seed head, or like a large daisy, and those will be 21 and 34, sometimes 34 and 55, depending on the size. And nature seems to find this pattern of numbers everywhere in the plant kingdom: 3, 5, 8, 13, 21. And how does the series formed? Well, from 3 and 5, you add the latest 2, 3 and 5 give you 8. And then you add the latest 2, 5 and 8 will give you 13, 8 and 13 give you 21, and so on. The series goes on. And you can start from 1 and 1 if you like, or 1 and 2. That's called the Fibonacci series because somebody who wrote about our decimal system, the way that you learn to do your arithmetic and write numbers in primary school now, was in fact quite advanced and only used by merchants around the Mediterranean about the year 1200. And Fibonacci used to wander around there and was very interested in the way that the Moorish Arabic merchants wrote their numbers, as opposed to a counter system or even Roman numerals, and their system worked quite well. And he wrote a book about it in Italy called Liber Abaci, the Book of Calculating, in 1202. And one of the little problems, it was really to say this is the way you do arithmetic and this is the best thing since sliced bread and it's a lot better than other systems. And it was written in the ordinary everyday Italian, and therefore it became a very popular book in Europe. So really he introduced the decimal system into Europe. And one of the little problems in there was to do with rabbits being put in a field. And it really was an exercise in terms of adding numbers up. You could add 1 and 1 to get 2, and 1 and 2 to give 3, and 2 and 3 to give 5. A problem in arithmetic. And it lay there forgotten about for a while until a French mathematician called Lucas in later 1800s found that the series had quite a lot of very nice properties, and so he named it the Fibonacci series. Now, it was known that it's in nature. You can see it in these spirals in plants. People didn't really know why until the 1960s or so, when in fact it was proved mathematically that it's the best way of packing leaves around a stem or petals on a flower or seeds on a seed head to get a uniform packing, and that gives the best packing for each of the seeds. There's only a number, and the spirals you'll see are the Fibonacci numbers. And where does phi come in? Well, if you take the ratio of these Fibonacci numbers, 3 to 5 is 0.6, and 5 to 8 and 8 to 13. The further you go on down the series, the closer and closer they get to this particular value phi. Or you can take it the other way around, 5 over 3 and 8 over 5, and then you're getting closer to that other number, 1.618. And in fact, you've no need to start off with 1 and 2. You can start off with any two numbers you like, 4 and 6, and add those. 4 and 6 give you 10, 6 and 10 give you 16. And the ratios of wherever you start, when you get the positive numbers, will always give you this golden section number. And that seems to be one of the clues that it's very interesting mathematically, that it ties up with a packing problem, a best way to pack things which nature has solved in evolution over the years. And it's not just in plants, you'll also find it in seashells. Here's a seashell that's been cut in half to reveal a spiral pattern. And each of these spirals from the centre is 1.618 times further away than the one before it, going down to the middle. In fact, this is a nautilus shell. And there's been some work done in America where somebody was interested in propeller shapes and thought, well, if I cut this and make it into a propeller here, does it have any nice properties? And he found, in fact, it does form a propeller that's 30% more efficient than the currently used propellers, and it's now being used by the American Navy under license from these people to form a propeller which doesn't